Alright, as I mentioned a few minutes ago, one of the things that we do with logarithms is we use them to solve exponential equations. Okay, we also are given sometimes equations that involve logarithms that we're going to be asked to solve also. So to solve any logarithm equation, okay, we just need to change it to its exponential form and then do something with the result. So this right here, that statement right there is very important. Okay, that's going to be your general rule for every equation that you want to solve that involves a logarithm. Okay, somehow or another we need to change it to its exponential form, okay, and then do something with the result. So if we look at this, if this is log x, then what base is here? 10. So if we want to solve this and figure out what x is going to make this true, we need to write base to the other side equals argument. Notice it's the same exact format as I use for evaluating logarithms. Okay, the base to the other side equals the argument. And if you do that, then a lot of times the answer is going to be obvious. Well, we already have x by itself, so aren't we done? Okay, and so what does x equal in this case? 10 to the fourth would be 10,000. Okay, and just like any other equation, this is checkable. If I put my 10,000 in here and I do log of 10,000, okay, I had better get 4. And don't we? Good. Now, another one over here on this side, if I have log base 2 of x equals 5 and I want to figure out what that x equals, okay, I would go again, base to the other side equals argument. And once again, in this case, when the x is the argument, okay, it turns out that the problem's already solved just by putting it into exponential form. So we'd get 32 equals x. Now, on your calculator, you can't do log base 2 of 32, so this is not checkable with the calculator in this case. Okay. But ultimately, if we follow the rules correctly, it should work just fine, just like that. Okay. Questions on the equation so far? Okay. Now, we do have, if you will, with me, look on page 305. We do have a special logarithm function. Okay, that is the inverse of our special e to the x function, okay, and that's what we call the natural log function. So the notation for the logarithm of this base is ln. We call it the natural log. Okay, this is also the same as y equals log base e to the x. Okay, so we don't ever write log base e to the x. We always write it as ln x. Okay, but this is an implied logarithm of the base of e. Okay. And another nice feature about a logarithm is you'll notice on your calculator you have an ln key right below your log key. So if you have to do the natural log of some number, okay, that's on there also. Okay, but ultimately that just represents the same logarithms that we've been dealing with, but it's base e instead of base 2 or base 10 or base whatever. Okay, so that e is a special base for logarithms, and they do have the function analysis here. And as you should suspect, since it's a logarithm, it looks like the other logarithms we looked at earlier. Okay, and all the information is here in this yellow box on your page 305. Okay, so let's look at some issues regarding natural logarithms. Once again, natural logs are going to be of the same rule set as we had originally for any logarithms. Okay, follow the same rules. These are just written specifically for the base e, okay, but they are just applications of the same rules that we looked at earlier. Okay, I already mentioned the graph of the logarithms. Notice that the natural logarithm, okay, has a larger base, if you will, or excuse me, a smaller base. E base, e is smaller than base 10. Okay, notice that the bigger the base is, the lower it is, if you will. Okay, the smaller the base is, okay, it's going to be a little bit higher curve, which we should suspect, knowing what we know about them being inverses of the exponentials. Okay, all right. Now, the other parts of this that we're going to deal with, okay, are just about transformations. Okay, the good news is that our transformations of logarithm graphs, okay, are exactly the same rules that we've been dealing with for any transformations. So if we're translating left, right, up, down, vertical stretch, flips, all that stuff is exactly the same information as we've had with our other functions. So knowing that, in this case, if I just had negative 3 ln x, that would be the 3 part would create a vertical stretch as normal. The flip here would be a flip over the x-axis, okay, and then the plus 2 over here would make the whole thing move up 2. So nothing different than what we did previous. Okay, so ultimately when we graph that thing, okay, it would turn out to be, they did it in parts here. The 3 and the flip give us this part, and then ultimately if we move it up 2, we can get our final graph, which is this one. Okay, moved up 2 from where we started. Okay. All right, and then finally, I want to talk real briefly about a couple applications that we use that involve logarithms. Okay, some of the things that we use in the real world here, we measure sound in decibels. Okay, the decibel equation is a logarithm equation. Okay, we also have a logarithm equation that is involved with the Richter scale that we use for earthquakes. Okay, and we also in chemistry, pH is measured with logarithms. Okay, so those are three specific examples of where logarithms are used in real applications that we might use in real life. Okay. So for your work for today, we're going to be working on section 3.3. You're using these properties of logarithms that we've studied so far. Okay. So that is that.